Okay, now today we are going to look at benzene. We are going to look at benzene. This is senior 5 chemistry, or you can call it aromatic. Aromatic hydrocarbon. Hydrocarbon. And specifically we are looking at benzene. Of course, there are many other aromatic hydrocarbons, but we are interested in looking at what? At benzene. We are going to say that benzene has molecular structure C6H6. Molecular structure C6H6. Well, one thing that we must appreciate is the fact that right from the 17th century, people have been trying to discuss benzene, trying to come up with a specific structure, structural formula for benzene, and most people would consider it as an alkene, but it is not possible to write an alkene with or a compound with multiple bonds in a straight chain. The only way to do that would be to form a ring, and in the late 17th century, Kekule structure suggested. Kekule suggested the structure which we later absorbed, calling the Kekule structure of benzene. He suggested that it is like this, whereby, of course, at every corner of the ring is a CH2. In that case, we would have a CH2, CH2, it is CH actually, CH, we have CH and CH. So you look at this, you look at that, then this, then that, and then that, and then lastly, of course, let me put this CH2 here, CH. He suggested that you could take this structure, of course, having these ones as double bonds. So there's a double bond here, there, and here. Yeah. So he gave us this structure. Of course, it comes about C6H6. If you see, there are 6 carbon atoms, and there are also 6 hydrogen atoms. So you could call it a Kekule structure. However, when you want to study in details this Kekule structure, which in that case would be 1, you could say 1, 3, and 5. 1, 3, and 5. Of course, you look at it and call it maybe a cyclohexene. So you would call it cyclohexene. But now there are 3 double bonds, and because of the 3 double bonds, it becomes hexene. The first double bond is on carbon number 1. If this one takes carbon number 1, this one takes number 2, number 3, number 4, number 5, and number 6. So the first double bond is on 1, the second is on carbon number 3, the third is on carbon number 5, Xe. So the Kekule structure would be cyclohex 1, 3, and 5 in. But when you look at the chemistry of the Kekule structure of benzene, it's not necessarily the same as the chemistry of benzene itself. And the reason why that happens is because when you look at the benzene ring in its reality, it can change form. And the reason why it can change form is because when you look at this structure, comparing it with this one, whereby the double bond is now here, and then another one here, and another one here, you realize that it is the same. It is the same structure. And the reason why this one becomes the same is because this bond can come here, this one can come here, and this one can come there. If this bond comes here, it becomes this. If this one comes here, it becomes this. If this one comes here, it becomes that. And this is very common, and it occurs continuously. It's more like a resonance because of the fact that every carbon in benzene is sp2 hybridized. sp2 hybridized. Its electrons in the s and the p orbitals, are hybridized. They are what? They are hybridized. I mean, they are promoted, they are excited. And because of the excitation, it brings about what we are calling resonance, which in that case will even lead to an explanation of what we call resonance energy that causes the stability, of benzene. Is that okay? And because this one occurs continually, we end up saying that we can also accommodate this structure whereby instead of having bonds in specific positions, we can just use a ring in the middle. This ring in that case would represent the fact that the electrons, are moving from one place to another. So at some point, the structure is like this. At some point, the structure is like this. So it just keeps changing, causing us to assume that benzene structure should have a ring inside, whereby the ring represents movement of electrons. So basically, that's it that we are going to talk about. Now, we want to look at what causes the difference between the Kekule structure and actual benzene. And that one we are going to call it the resonance energy. We are going to call it the resonance energy. Now, when you look at resonance energy, I'm going to explain it. Now, if you have this compound here, and how are we going to call this compound? Of course, this is cyclohexene. If I want to hydrogenate cyclohexene, of course, hydrogenation is simply addition of hydrogen in presence of a catalyst. Probably I'm going to use nickel at 150 degrees. That means that one hydrogen will come here, another one here, leading to formation of an alkane. In that case, we shall call it cyclohexane. Now, what will be the energy change for this reaction? When we look at the energy change, here, delta H is equal to minus 119 kilojoules per mole. That means if I add one hydrogen atom across the double bond, I mean two hydrogen atoms across the double bond, that will be the energy change that takes place, meaning the reaction is exothermic. What if I would have maybe the Kekule structure, whereby I have 3 double bonds. I have 3 double bonds. That means I'll need to add a pair of hydrogen atoms across each double bond. So I'll bring 3 hydrogen molecules. 3 hydrogen molecules still in presence of nickel at 150 degrees Celsius, or you can use platinum or palladium at room temperature. Still, I am expected to form an alkane. Is that okay? Therefore, it means the change in energy there is going to be this times 3. Then times 3. Do you see that? The reason why we are saying it's times 3 is because here we were adding hydrogen across one bond, one double bond, but now here we are doing it 3 times. And therefore, even the energy that accompanies there is supposed to be that. And the value is minus 357 kilojoules per mole. Is that okay? And therefore, it means that the enthalpy of hydrogenation of the Kekule structure of benzene is minus 357 kilojoules per mole. So it means that even if we were to consider benzene in this structure, therefore the enthalpy of hydrogenation of benzene is supposed to be this. However, the experimental values show that the hydrogenation of benzene is lower than this. That means that the hydrogenation of benzene, in reality, if I was to represent the hydrogenation of benzene using a ring, plus 3 hydrogen gas in the presence of nickel at 150 degrees Celsius, leading to the formation of cyclohexane. The enthalpy of hydrogenation of benzene is actually minus 207 kilojoules per mole. That means the enthalpy of hydrogenation of benzene is lower than expected. It is expected to be 357 if we were to consider benzene as a Kekule structure. However, in reality, it is actually minus 207. That means that benzene is actually more stable than the Kekule structure. Why? Because replacement of the double bonds in benzene does not evolve or does not liberate a lot of energy compared to that of the Kekule structure of benzene. Meaning you can easily hydrogenate cyclohex 135 in fact it's supposed to be tri 135 tri-E. Try to mean that there are 3 double bonds. It is easier to hydrogenate the compound than to hydrogenate the benzene ring. So we are going to say the difference in the energy of hydrogenation is actually what we are calling resonance energy. So the resonance energy of benzene, the resonance energy of benzene in that case is going to be what we expect, minus 357 minus the actual, which is minus 207 kilojoules per mole. And the answer there is minus 150 kilojoules per mole. So this one we call it the resonance energy of benzene. This is the energy that would be responsible for the stability of benzene. So we can simply say that benzene is more stable than expected according to the structural formula of benzene, which was suggested by a man known as Kepler. Now we are going to look at how to produce benzene. We are going to look at how to produce benzene, or the synthesis of benzene. We are going to look at synthesis of benzene. We are going to say that if we are going to produce benzene on a large scale, we are going to have to get it from petroleum by fractional distillation. So benzene can come from petroleum by fractional distillation. However, the laboratory preparations of benzene, or the synthesis of benzene in the laboratory, we have three main sources of benzene. The first one, we are going to call it decarboxylation. We are looking at decarboxylation of sodium salt of benzene. Decarboxylation of the sodium salt of benzene. In that case, we are going to require to have. So when we are representing benzene, we can use a Kepler structure, or we can use a ring. Any that you use can be accepted to be correct. However, when you are drawing this ring, you must make sure at least that the bonds are almost equal, because of course you cannot be accurate when you are drawing, but you have to give an impression that the bond lengths are equal. And also the ring inside, there are some who draw this. This one will be wrong. The ring must be close to the outer bonds. Then there are some who draw this. This one would be wrong. Why would it be wrong? Because the bonds are not equal. Whereas the studies show that the bonds in benzene are what? Are equal. The bonds in benzene are equal. So I have the benzene ring. I'm going to add a carboxylate group. So this one you can call it sodium benzoate. So how do you decarboxylate sodium benzoate? We are going to use soda lime. Soda lime is a combination of sodium hydroxide and calcium oxide. Soda lime. So I can write soda lime. Instead of writing soda lime, I can also use sodium hydroxide stroke calcium oxide in presence of what? Of heat. This method, we have also seen it in the preparation of alkanes. It is used to remove the carboxyl group on the compound, and therefore we just remain with our benzene. I hope that is okay. That is our first step. Our second step, we can get it from phenol. We can use zinc. In presence of heat, we are able to reduce phenol to benzene. So you can say our second one is reduction of phenol. The second one is reduction of phenol. Of course, phenol is benzene. benzene with an OH group. This is phenol. Benzene with an OH group. So what I need to do is to remove the OH group on phenol. And you have said all I need to do is to add zinc and then do what? And heat. That will establish, or it will bring about reduction of phenol directly to what? To benzene. Phenol directly to benzene. I said you can use a ring, or you can use the Kekule structure. Let's look at our third method of preparation of benzene. We can talk about polymerization. Our third one is polymerization of ethane. Polymerization of ethane. Polymerization of ethane. Here we must use organonickel catalyst. We must use organonickel catalyst. We are using organonickel catalyst in the presence of a temperature of about 60 to 70 degrees Celsius. So we have CH, triple bond CH, where some can write the H behind, because the triple bond is essentially between carbon to what? To carbon. So we are using organonickel catalyst. Organonickel catalyst at 60 to 70 degrees Celsius. 60 to 70 degrees Celsius. This leads to the formation of benzene. It is more like polymerization. So in this case, in fact, I might need 3 molecules of ethane. 3 molecules of ethane. I combine them together to form 1 molecule of benzene. So those are some of the ways in which we can prepare benzene. The first one, we have talked about decarboxylation of sodium benzoate. Then we have looked at the reduction of phenol, and then lastly we have looked at polymerization of ethane. However, there are many other methods of formation of benzene, which you can always look out for in textbooks. Now I want to look at the physical and the chemical properties, of benzene. Of course, when you look at the physical properties, we are more interested in the properties that are actually physical about benzene. Properties such as we are looking at the melting point, the boiling point, the color, the smell, those are the properties that we are interested in, the solubility and density, etc. We want to look at the physical properties of benzene. So benzene is actually colorless. Is that okay? However, it has a characteristic smell. We are going to call it aromatic smell. So it is a colorless liquid. Colorless liquid. It is a colorless liquid with an aromatic smell. Okay. Yes. So it's a colorless liquid with an aromatic smell. Do you see that? It's a colorless liquid with an aromatic smell. Secondly, secondly about benzene, it cannot be soluble in water because it is non-polar. So it is insoluble. It is insoluble in water. Insoluble in water. But of course soluble, but soluble in organic, soluble in organic solvents. Soluble in organic solvents. Of course, when we talk about organic solvents, we are talking about maybe trichloromethane, etc. Trichloromethane, we have even tetrachloromethane, we have naphthalene, camphor. So we have very many other organic solvents. Of course, these ones should be at least non-polar. Is that okay? Then thirdly, we're going to talk about what happens when we burn benzene. Because of its high carbon to hydrogen ratio. Now we have seen carbon 6, hydrogen 6. Because of high carbon to hydrogen ratio, due to the unsaturation of benzene, when you burn it, it will always give you soot. It will always give you a sooty flame. So that means it burns with a yellow sooty flame. With a yellow sooty flame. It burns with a yellow sooty flame. Of course, since it is a combination of hydrogen and carbon, being a hydrocarbon, it produces carbon dioxide and water. But of course, the sooty flame comes because of the incomplete combustion of carbon, which comes as a result of the high concentration of the carbon atoms in the compound, and also, of course, the unsaturation in benzene. So basically, those are some of the physical properties that we can look out for. But we have many other which you can always look out for. Let's now talk about the chemical properties. Let's talk about the chemical properties now. Let's talk about the chemical properties of benzene. About the chemical properties of benzene, we are more interested in the reactivity of benzene. Chemical properties of benzene. Chemical properties of benzene. Here we are more interested in the reactivity of benzene. How does benzene react? How does benzene react? We are going to look at a few of the reactivity of benzene. First, the first two we are going to look at how benzene reacts with acids, and the first acid we are calling it nitric acid, and that one we are going to call it nitration of benzene. Nitration of benzene. We are going to call it the nitration of benzene. What is basically the nitration of benzene? When you look at nitration of benzene, like the word says, it is a reactivity of benzene with the concentrated nitric acid. But of course, this is going to be in the presence of sulfuric acid. So sulfuric acid is going to act as a protonator of nitric acid, and it is going to facilitate the formation of a nitro group, which is going to be our electrophile that shall be attacked by the benzene. i.e., we are saying that this is the reaction. This is the reaction of benzene. The reaction of benzene with concentrated nitric acid, with concentrated nitric acid, in presence of concentrated sulfuric acid. In presence of concentrated sulfuric acid, we are going to have a temperature at 60 degrees Celsius. At 60 degrees Celsius. In fact, the temperature can be 55 to 60, it can be allowed. So we have 55 and to 60 degrees Celsius. 60 can be allowed, 55 to 60 can also be what? Be allowed. i.e., we are having this is my benzene ring. So I am adding, we are having nitric acid, conc nitric acid, we are adding conc sulfuric acid, or sulfuric acid. I was saying the temperature is 55 to 60 degrees Celsius. This leads to the formation of nitrobenzene. It leads to the formation of nitrobenzene. Of course, I said we can use this, we can use the chemical structure, any can work. And sometimes we interchange the usage. But it's better when you begin with the ring, you maintain the ring. When you begin with the chemical structure, you maintain the chemical structure. Now let's look at the mechanism of this reaction. The mechanism of this reaction. We want to look at the mechanism of this reaction. Now we are going to begin with the concentrated sulfuric acid. Sulfuric acid, when it is conc, it is a weak acid which partially ionizes to give hydrogen ions and the hydrogen sulfate ions. Now the hydrogen ions are going to react with nitric acid, so our nitric acid is going to secrete in that way. Of course, the OH will go with the hydrogen ions, and then the nitro will remain alone, leading to the formation of water and what? And the nitro group. Water and the nitro group. Now, remember what we said. We said that our benzene has a what? A ring. This ring is full of electrons. Is that okay? It's full of electrons. These are the localized electrons in the ring. And because they are delocalized, we can simply say that they can actually even attack an electrophile. Remember, in organic chemistry, we are always looking out for the nucleophile and its ability to attack the electrophile. A nucleophile is simply an electron-rich species, and because the benzene has delocalized electrons in that ring, then we can say that it is also a nucleophile, and these electrons are able to attack the what? The electrophile. In that case, our electrophile being the nitro and the nitro group. So it is going to come and attack that nitrogen in that case. Of course, in what we call a dative bonding kind of situation. In dative bonding, the electron-rich species acts as a donor and it donates electrons to the electron-deficient species, which in this case is the nitro group. So what will happen to our ring? Our ring has used the part of its electrons. Our ring has used the part of its electrons to attack the nitro group. Therefore, the ring will become unstable and will become partial. It will not be complete. So I'm going to do that. And because it has attacked nitrogen, therefore it means there is now a partial lack, or there is a lack of electrons inside the ring, and then we will just use a positive charge to show the lack of electrons, to show that some of the electrons which were here were used to create a bond between carbon and nitrogen. And that bond, I'm going to put it here. So that is the bond that we have actually formed. The bond that we have actually formed. But remember, on a benzene ring, on every corner, like we said, there is a CH. And that means that this carbon has an H. That carbon has an H there. Do you see that? Remember, every time I draw this, I'm simply saying on every corner there is a CH. There is a CH on every corner. But for convenience purposes, we do not put the CH. We just use the structure like that. That means if the bond has been created on this part, I'm going to show you how the mechanism would go with the Kekule structure, and you'll be able to appreciate it. But there is a hydrogen. So I have put the hydrogen here. Some people might wonder, where is this hydrogen coming from? It comes from the fact that on every corner of the benzene ring, there is a carbon and a hydrogen. So the nitro group has been attached to this carbon, but there is still what? A hydrogen. So this hydrogen atom is going to be lost as a proton, and these electrons that form the carbon-hydrogen bond are going to come and try to complete or to neutralize the positive that has been formed in the ring. So the electrons will come back. The electrons will come back into the ring. What do we form? We have now a loss of a hydrogen proton because it has left the electrons which have come back to complete the what? To complete the ring. So the ring now is complete. And then we will have our nitro group there. We'll have our nitro group there. So you can see that this is the mechanism. What would happen if it was a Kekule structure? If I was to use the Kekule structure, I can also demonstrate what would happen there. Of course, the Kekule structure has the bond here and the bond there. Is that okay? It will still have to react with the nitro group. In that case, the double bond is the one that is going to attack. Remember, a double bond is what? A double bond is now, in that case, two pairs of electrons. And the electron, it means the this side is rich in electrons, and therefore a double bond can easily attack an electrophile. In that case, it means that this bond is going to establish a bond between any of these carbons with nitro. So I'm going to establish the bond between this carbon here and the nitro group. So this is what we're going to have. So this bond is still there. This one is also still there. However, this one has been used to create a bond between carbon and the nitrogen. So I'll put it there. I'll put it there. Is that okay? Of course, there is still a hydrogen here. We have to appreciate. However, this carbon here, it has lost its electron. Remember, a bond is always a pair of electrons shared by two atoms. It means if the bond has been lost, the electron that was being contributed by this carbon has gone with it. And therefore, this carbon atom has lost an electron. And because it has lost an electron, it becomes positively charged. So I can put the positive here. Someone can choose to put the positive outside. It doesn't matter, as long as you have indicated that the carbon on this corner is the one that has a positive. In that case, I can break this hydrogen bond in order to neutralize the what? To neutralize the positive by creating another bond. Where the previous one was, I'm just breaking the hydrogen bond to create that bond again. So I'm still losing H plus, leading to the formation of that bond there. There's already bond here, and then the nitro group, So, whether you are using the chemical structure or the ring, the mechanism will just remain the what? It will just remain the same, as you can see. The only difference comes here. And most students, especially most students who use the ring, they are always confused. But you shouldn't be confused. This just shows that the ring is not complete. And also, when I put the positive in the middle, this actually shows that the positive can alternate between different positions of carbon atoms. So it shouldn't really confuse you, because these electrons are delocalized. So that is nitration. That is nitration for you as the first reactivity of benzene, whereby benzene reacts with nitric acid in the presence of sulfuric acid at 55 to 50 to 60 degrees Celsius. To 60 degrees Celsius. Sulfonation of benzene. Sulfonation of benzene. Sulfonation of benzene. So we want to see what happens with sulfonation of benzene. Of course, with sulfonation of benzene, we are more interested in the reaction between benzene and concentrated sulfuric acid. However, it must be fuming. The sulfuric acid must be fuming, and also the temperature should be between 35 degrees Celsius to 50 degrees Celsius. 50 degrees. I.e., we are talking about the fact that benzene, maybe I can use the chemical structure now. I'm going to use concentrated, or I can just do this. Corn, sulfuric acid. In fact, let me use fuming instead of corn. Fuming sulfuric acid from at a temperature of 35 to 50 degrees Celsius. What will happen is we are going to form benzene sulfonic acid. Benzene sulfonic acid. This one is called benzene sulfonic acid. Benzene sulfonic acid. So, sulfonation of benzene requires the reactivity of benzene with fuming sulfuric acid at a temperature of about 35 to 50 degrees Celsius. Let's look at the mechanism. We want to see how the reaction takes place. Let's look at the mechanism. So in the mechanism, we are going to have two sulfuric acid molecules. They are going to form sulfur dioxide. They are going to form a hydroxonium ion, and then they are also going to form the hydrogen sulfate. They are going to also form the hydrogen sulfate. Now what will happen is that the sulfur trioxide is the electrophile that will be attacked by the electrons in the benzene ring and spark off the reaction between sulfuric acid and benzene. So our reactivity mechanism will continue from here, whereby here I'm showing benzene. So I am adding, I am using sulfur dioxide. However, allow me to show the atoms arrangement in what? The atom arrangement in sulfur dioxide. So I'm saying that the double bond in the benzene is going to come and attack the sulfur, the central atom. When it attacks, this bond will be forced to withdraw to oxygen. That means that we shall form. So this compound here has come here, right? So it will come as SO3, but because this pair of electrons has been taken by this oxygen, so the oxygen will have an extra electron. An extra electron, therefore one of the oxygens will become negative. One of the oxygens will become a negative. But if you find it confusing, still take it as you have oxygen here, you have oxygen here, and then this is O minus. So this is exactly our SO3 minus. Of course, we still have hydrogen here, because you said on every corner there is a carbon and a hydrogen. And because the bond, this bond has formed a bond here, then this carbon here will have lost an electron and it will become positive immediately. These ones still have their what? Their bonds. Still have their bonds. So what will happen is that this hydrogen will break off in an attempt to form the bond that we had removed. And then now this hydrogen will be shifted. Instead of it being lost, it will be shifted and it will come to this oxygen. And then we shall form, so this one we shall call it a hydrogen shift. And then we shall call it a hydrogen shift. H plus shift. It is shifting from here to there. And then we shall form our benzene sulfonic acid. This one has been replaced. So it is O3, but this hydrogen has come here, so we call it H. We put there H. However, some can write the same here, and then they just bring this hydrogen, they replace it here. However, it is just the same. Here, I'm not showing the specific structure formula, but still it represents the same thing. So that is the mechanism that will be able to show the sulfonation of benzene. If you want to sulfonate benzene, that's what you're going to do. That's the mechanism of reaction that takes place. Let's look at another reactivity of benzene. We are going to look at halogenation of benzene. We are going to look at halogenation of benzene. Halogenation of benzene. Halogenation of benzene. Of course, it comes from the word halogen, and you and I know that halogens are group 7 elements. Fluorine, chlorine, bromine, iodine. So, this occurs in the presence of a Lewis acid. So this is the reaction. This is the reaction. This is the reaction between benzene and halogens and halogen molecules. You can talk about bromine. You can talk about chlorine. Those are the ones that are most common. We rarely talk about halogenation with the iron. Halogen molecules in presence with, of course, with benzene, in presence of Lewis acids, in presence of Lewis acids. The Lewis acids we are dealing with can be e.g. we can have iron 3 halide. We can even have aluminium halide, where in that case X stands for chlorine or what? Or bromine. Chlorine or bromine. Well, sometimes it might be in presence, of only iron. Of course, a Lewis acid would consider it as a compound that can accommodate more electrons, and therefore it has space where it can accommodate more electrons. So we have a few of the Lewis acids. In that case, iron 3 chloride can work, iron 3 bromide can work, aluminium chloride can work, but also aluminium bromide can work. So we are just going to pick out any of the examples. Remember that you can also use iron alone, but in that case it will be better to use chlorine and iron. So if you are reacting benzene with chlorine in presence of iron, remember iron will first react with chlorine. It will first react with chlorine in presence of what? It will first react with chlorine to form iron 3 chloride. And that iron 3 chloride can react now or can act as a Lewis acid to facilitate reaction to take place. So, e.g., we're going to have a reaction between benzene, and chlorine. Reaction between benzene and chlorine in the presence of iron 3 chloride. This will lead to formation of chlorobenzene. This will lead to the formation of chlorobenzene. Can we look at the mechanism? Of that reaction? Let us look at the mechanism of that reaction. We are going to have benzene. We are going to have our benzene ring. So this is our benzene ring. So I'm going to bring my chlorine. But remember, a chlorine molecule is made up of chlorine atoms. Chlorine atoms, there are two. It is a diatomic molecule. And they share a covalent bond. But there is a possibility that this covalent bond can be polar in just a small minute second. That this can be partially negative, this can be partially positive. You have seen that between the reaction of halogens and alkenes, it is still possible here. However, sometimes you might show the partial charges, sometimes you may not have to show the partial charges. We have said in the presence of iron 3 chloride. So what will happen is, in the moment when this one is partially positive, this double bond in benzene will attack it, and then this bond of the chloride will break off, and it will join on the Lewis acid and 3 chloride. Iron 3 chloride. Do you see that? Because iron 3 chloride as a compound is able to accommodate more electrons from any ligand, leading to the formation of this chloride atom has come here, replacing the hydrogen which is still there. This one has become positively charged. There is a bond here and a bond here, of course, plus now the Lewis acid shall become like this. But remember, the chloride that came with an extra bond. This bond was broken and taken away by this chloride. So the chloride will make the Lewis acid negatively charged. It will make it negatively charged. So what will happen is this hydrogen will break off, trying to come back there. So will lead to the formation of this one comes back, this one comes back, like that. In fact, in this case, we might end up releasing a hydrogen chloride molecule. Why? Because of the chloride ion around here and the hydrogen atom, the hydrogen ion that has been released due to the formation of the double bond there. So they might end up forming hydrogen chloride, which can represent a byproduct of the reaction, leading to the formation of chlorobenzene. So we are going to see many other reactions of benzene, but for now, let's first see